on his employer, who apparently was a very kind man. Now, to be an apprentice in those days, you had to pay because you were learning a trade. However, this bookbinder he worked for realized that the family had no money or very little money, and so he offered to take on Michael as an apprentice for free, which was a very great thing. And the job allowed the young man to read lots of books when he was there working. And he found some articles by a chemist that were of interest to him. And his older brother, James, again, who was a much more successful blacksmith, bought him some tickets, paid 5 shillings, which was not a small amount of money, for him to attend some talks at the Royal Institution in London about chemistry and science in general. And when he was there, when Michael was there, he met lots of other young men. There weren't, unfortunately, very many young women. But he learned a lot about what we now call physics and chemistry, which was, of course, in those days just called natural philosophy. Now, one of the customers at the bookbinders was so impressed with Faraday that he bought him some other tickets to attend 4 lectures that were given again at the Royal Institution, but this time by the director of the Royal Institution, Sir Humphrey Davy, probably the most famous scientist in the world at that time. And he did that, and then the apprenticeship ended in the year 1812. And after about 7 years, and he found a paid job, which was, of course, better, except the person he was working for was not very nice, and he didn't get along very well with him. And so he wanted a better position, so he wrote to Humphrey Davy, and he was a very fastidious note taker of lectures, and so he wrote to Davy and included the notes he had taken from the lectures, and Davy was very impressed. But he had no money, which is not unusual in scientific institutions, so he couldn't hire him. But the very next year, there was a brawl that occurred in the Royal Institution where one of the lab assistants got involved in a fight and he was sacked. And so Humphrey Davy then offered the position to Faraday. And the pay was a guinea a week, 21 shillings a week, and it included a room that he could live in. And so he could leave the family home and live in the Royal Institution. And he made a very significant impression upon Davy, who's, now that I have, there's a picture of the Royal Institution as it was and as it is, the only difference being the mode of transport that's in front, from horse and carriage to cars. This is what Davy said about the young man. His manner is position didn't all come out, is active and cheerful, and his manner intelligent, it said. Now, in the autumn of that year, it's 1813, in the autumn of that year, Davy was invited to go to the continent, to travel to France and Italy, to tour and confer with other scientists. Now, the years 1813 and 1814, of course, there was a war, Napoleonic War between England and France, or Britain and France. But Davy was a scientist and natural philosopher, and that was considered to be independent of politics, and so he was highly welcomed by the French, despite the fact that the countries were at war. and he was able to use the lab facilities of the French, and there he discovered a new chemical element which we today call iodine. In 1814, they moved from France to Italy, where he was equally well treated. And the only problem there was that Davy was traveling with his wife, and his wife didn't like Faraday for some reason, I don't know quite why, but that made the young man pretty unhappy. However, they were in Italy, and then in March of 1815, Napoleon, who had been exiled to the island of Elba, escaped, and so war broke out again between Britain and France, and so the British group fled back to London quite quickly, but Faraday had impressed his boss so much that he was appointed as assistant and superintendent of the apparatus of the laboratory, and given a pay rise of now 30 shillings a week and a better room of accommodations. Several years later, by 1821, he was superintendent of the house laboratory, and by 1825, when he was 34 years old, he was director of the entire Royal Institution. So in the space from 1813 to 1825, in just 12 years, he had this uneducated man, this kid who dropped out of school at the age of 13, was the director of the most prestigious scientific research laboratory in the country. Just really quite remarkable. And his salary was now £100 a year, which is a decent salary in those days. He had worked obviously very hard in order to do this. He had learned how to do some serious chemical analysis, and he had learned how to, had helped on a lot of demonstrations and things. But the work he had done had changed his relationship with Humphrey Davy considerably. And the reason for this happened at an opportunity for him to do independent research that happened in 1821. Because in 1821, in Denmark, there was a school teacher named Hans Christian Ørsted. And Ørsted discovered a relationship between electricity and magnetism, the first time that this had been done. Now, in the 17th and 18th centuries, the only thing that was known about electricity was static electricity, which you could get by rubbing your feet or rubbing by friction, by rubbing objects together. But then in Italy, a man named Alessandro Volta invented the battery, or the voltaic pile, as it was called. And you could start to do experiments with flowing electricity, with electrical currents. Electricity is an enormously strong force, hugely much stronger than gravity. The reason we don't normally notice that is because in gravity, there is only one kind of mass. It's us, it's positive mass. And therefore, given the number of atoms in us, which is enormously large, the force seems reasonably big. Electricity doesn't show that because there is both positive and negative forms of electricity, and in most matter, they balance. And it is only when the balance is slightly off, such as what we see in a flash of lightning. Only in such cases do we normally notice that. The number in static electricity, in friction, the number of electrons in a material is so enormously large that the change of a few trillions of electrons is so tiny that that amount is what we can get by rubbing our feet along the floor and the shock, the kind of shock we get. By the way, nobody that I know likes that feeling of touching a doorknob and getting a shock. And since physics does have some practical application, I can show you how to never have that happen to you again. Because the reason it hurts is because we touch it with our hands, and our fingers have are our sense of touch. They've got lots of nerve endings. So what I do in the winter time when the air is dry and I come up to a metal object, I touch it with my knuckles. These have very few nerves in it, and I still get a spark, but it doesn't hurt. Then it discharges, and then I can turn. A word to the wise. So there is some practical knowledge. What Ørsted discovered, because we can now have motion of electric charge, we could have a current, as it's called, is what he had discovered is a relationship which looks as follows. If he took and passed a current through that copper wire, the magnet underneath would rotate such that it was perpendicular to the current. It doesn't matter what north and south is, it would rotate in that direction. This was the first indication that we ever had of a relationship between electricity and magnetism, and it caused a huge surge of interest suddenly. And Faraday jumped at the opportunity and wrote a review article, and he found not only this effect, but then he found that if he had a reversal, that a wire carrying current could rotate around the pole of a magnet, something we will talk about, and was the first indication of the creation of an electric motor. Now, this also was the beginning of a serious change in physics, because up until this time, the only science of physics was due to Isaac Newton, and it had forces and masses and accelerations and velocities, and that's what was talked about. But now, starting in the 19th century, and partly really due to Faraday, we have the idea, a completely different idea of energy and the conservation of energy, which is the single most important fact in all of physics. And energy exists in an enormous number of different forms, in motion, in chemistry, in electricity, in magnetism, in heat, in atoms, in nuclei. And all of these forms of energy can be traded one for the other, but what cannot happen is the loss or the creation of energy. There is a fixed amount, and all we can do is change forms from one to the other. Faraday published some of his results, and this led to problems in his relationship with Humphrey Davy, because friends of Davy said that Faraday didn't acknowledge Davy's contribution. So Faraday, who thought that science was somehow a pure form of intellectual activity, it's a human activity, and human beings are difficult animals. And then this happened in 1821. Again, 2 years later, it occurred again because friends of Faraday put him up for nomination as a Fellow of the Royal Society. Humphrey Davy was the president of the Royal Society. He opposed Faraday's election, but Faraday was elected anyway, and that made relationships between the two men even more sour. And it wasn't really until Davy died, which was in 1829, that Faraday got truly scientific independence. But Davy made a huge impact and an important impact on Faraday's life. One of the things that he did, by the way, is he encouraged at an earlier stage Faraday to help found the Athenaeum Club. And any of you who might know about London would know that the Athenaeum is still a very exclusive and fancy club in London. So by 1825, he was the director, and one of the first things he did was start a series the next year, 1826, of Friday evening discourses, public lectures on scientific topics, something which became a serious part of the Royal Institution's history. He also arranged for exhibits at the institution's library. And one of these exhibits included materials that had been brought back by a man named Sir Stamford Raffles. Some of you may know the name Raffles. He was a man who was looking for a naval base for the Royal Navy in the eastern Pacific, and he discovered an island off the south coast of the Malay Peninsula, and in 1813 founded the city we now call Singapore. That's why there's a Raffles Hotel, of course, in that city. I have a painting of Faraday lecturing at one of his Friday night things, and the audience was really significant. There's Prince Albert, the husband of Queen Victoria. There is his wife in the corner. There are lots of women and as well as men. There are even some children. These were very popular. He also started and founded the Christmas lectures, which still exist. And in fact, they not only exist, they exist in the very same theater where he lectured back in the 1840s. The only difference being the electronics, and they've reupholstered the seats, I think, since 1840. But aside from that, it's really the same. Now, what he discovered back in 1821 was that he could make a wire rotate about a magnet, which, as I said, is the heart of electric motors in our day. But making an electric motor is not a trivial thing. And so let me show you some of the things. This is a DC motor. There was only direct current DC in his day, of course. And DC motors are still quite common today. We all have one in our cars. They are the starter motor that turns the engine over to start any car motor. Let me show you the problem. So you just have a magnet and a coil of wire, and you run a current through it. The problem is that when you, I wish I had a laser pointer, but when you rotate, that would go this way and then back, and because the current would be in the opposite direction. And so it wouldn't be very helpful. So what is done is to have the connection in this so-called split ring commutator such that the right-hand side is always connected to the positive terminal in the battery, and the left-hand side always, so that when it flips 180 degrees, that red side is now a green side because it's attached to that wire. So it's a little complicated, but that is how it works. There's a closer up picture of a copper brush, a carbon brush, sorry, and copper for the conduction of the electricity. And this work unfortunately soured some of the relationship between the two men. But what Faraday had, or Ørsted had showed, was that an electric force, electric current, could create magnetism and affect the bar magnet. So if electricity could create magnetism, then everybody thought that magnetism could create electricity to be the opposite effect. And so everybody looked for it and nobody could find it. It was very hard. Faraday did not give up. And he, in fact, then discovered the way in which magnetism can create electricity, and it's called electromagnetic induction. It took him 10 years of very difficult work. It didn't happen until August of 1831. And this is what he did. There's a sketch from his notebook, and there's a more modern picture of it. And let me try to explain some of what happens. Here's a battery and an iron ring. Okay? And the battery is connected to a coil of wire that goes around the iron. Okay? And that's it. And once I close the switch, current will flow in that side of the coil. Then on the other side of the coil, I have just a coil of wire, and that's connected to a thing called the galvanometer, or an ammeter, if you like, over there. Okay? And it has no battery, and nothing flowing, nothing happening in it. And what Faraday noticed is that there is no effect. Right? First, the switch is open, so there's no current. But when he closed the switch, the ammeter flipped. Once the switch was closed and current was flowing, nothing happened. Okay? There was no motion. Then when he opened the switch, it moved again, but it moved in the other direction. Okay? So there was an effect. So what he's done is to create, by running an electric current on the left side, he created an electric current on the right side. And that happened only when the switch was closed or open, only when the current started or stopped. He could generate an electric current. And this is the foundation of all the electric technology for generation that we have today. This is all invented by Michael Faraday. And we have gone from this little experiment of him opening and closing a switch into enormous generators that are driven, machined to clearances of millimeters, and driven by huge torrents of water falling down a dam, or by steam, steam. And it has certainly powered one of the greatest revolutions in human history, I think. And one, of course, becoming even more crucial in these days of global warming. It's quite an amazing and hugely important discovery. He did also, in this case, what has happened is he created a current by opening and closing the switch. In this case, he did a similar sort of thing. He took a magnet and he just inserted it inside the coil of wire, and that made a little current. When the thing was at rest inside, nothing happened, and then when he pulled it out, there was again a current. So again, the change, and what he's doing is converting mechanical energy, a change of energy, into electrical energy. And so from that, we now have that. It's the same thing going on, mechanical energy rotating in this time to create electric current. Faraday wrote over 30 papers on the generation of electrical current. And to talk a little bit more about my science, I want to try to understand a little bit of, or discuss a little bit of what's going on. So I want to take a thing that most people have ever seen. I take a simple bar magnet, and I put a sheet of paper on top and sprinkle iron filings over it. And I get this pattern, okay? And many of us have seen such a pattern. And these lines, Faraday, this is Faraday's experiment originally, he calls these lines of force. Now, in a battery, we're converting chemical energy into electrical, into motion, mechanical energy, which is the motion of electrons in a wire, as we now understand, and that's what we call electrical energy. So again, it's the conversion of one form of energy into another. But this arrow points to a piece of iron at that point. Now, the iron is only there to show what's happening, but these lines, if you like, are there in any case. How does that piece of iron know the magnet is there? It's not touching it. Every force we have normally, the forces we understand, mechanical forces, involve contact. I push something. Okay. How does that piece of iron know that the magnets are? Or in other words, or another example, the Earth revolves around the sun in almost a circular orbit. The sun is 150 million kilometers away. How does the Earth know the sun is there? How do we get this effect? That is a puzzle. Newton knew that the sun affected the Earth and with the force of gravity, but he, brilliant man that he was, did not understand how that could happen. And he even wrote in the Principia in Latin, hypothesis non fingo. I make no hypothesis about, I do not understand how it happens. Now, Faraday drew the lines. There's his picture of these lines. And he talks about the fact that I get an effect if I cut through the lines with a wire. I can generate a current in that wire. And the idea of imaginary lines is something that we use a great deal. For example, we have on Earth lines of longitude and latitude, and we have isothermal lines on weather forecasts. And so this idea which Faraday invented of the idea of what he calls lines of force became in the hands of significant mathematicians like James Clerk Maxwell, about whom we'll talk tomorrow, became serious mathematical techniques for dealing with forces and what are called fields, to use the modern terms. Faraday, of course, as I said, had very few mathematical skills. The French, who were highly mathematical, used to make a bit of fun of him, but he was smarter than any of them. And experiment need not quail before mathematics. I take that very seriously because I did experimental physics and like finding some of the mathematics that's used today difficult to understand. In trying to teach students about magnetism, this is often a very difficult subject because it is inherently a three-dimensional problem. We have three different, we have a relationship between motion, which has a direction, with the magnetic lines, which have a direction, and an electrical current, which has a direction. And these three lines, or vectors, if I use the mathematical terminology, they form a three-dimensional system. Okay, so the direction of motion, say, is up. The current, the magnetic field line is in this direction, and the current is in that direction. And so what people do when they teach this, a course like this is they make the so-called right-handed rule. And so I take my fingers and first finger field, and this is the current direction, and then this becomes the direction of motion. And so if you give an exam, for example, watch students all sorts of things, it's difficult for them, but it's amusing for the person standing in front of the class. Now, it's not, to emphasize, it's not the presence of a magnetic field, but it is the change of a magnetic field. This is a whole idea of energy as a change of something. And it is in the 19th century that the concept of energy becomes so powerful. And it is largely due to an unmathematical genius, Michael Faraday. What he discovered in that picture is a transformer. This is the first electrical transformer. And the start of a current on the left-hand side creates a current on the right-hand side, but only with the start or stop. And so I can flip the switch up or down, or I can have a continually changing current on the left-hand side, which is what we call alternating current, or AC. And that's why we have used particularly AC or alternating current in our homes, because it's always changing. There were in his day many different kinds of electricity. The static electricity was called frictional or rubbing electricity. And then there was voltaic electricity. And Volta's discovery of the battery came about because a man whose name again is used, Volta, of course, Luigi Galvani, the galvanometer, was an anatomist, and he had been dissecting the leg of a frog with an iron scalpel. And the frog, of course, just was a leg. And he had the frog leg lying on a copper plate. And when he cut into the thing, the leg twitched. Must have scared the hell out of him, imagine. But, and what he was doing, of course, there are nerves in the leg, even though it's dead, and he was making an electrical current. And of course, the leg moved. And that's what moves us, is electrical current in our nerves. There were all these different names, but of course, there's just electricity, which is the motion now that we understand of electrons, these negative particles, that in a wire, in a metal, in most atoms, the electrons are stuck tightly to the protons in the nucleus. But in metals, there is always one or two electrons that are relatively free to move around. They're not very well attached. And if I put a difference of potential energy on the ends by a battery, they will move through the wire. And that's, of course, the discovery of the electric current. Many of the words we associate with electricity and chemistry were invented by Faraday, words that some of you may know: ion, cation, electrode, cathode, anode, electric light, electrolyte. These are all actually basically Greek words, which he didn't know himself, but he got help from university people and to name things that he discovered. The 19th century, of course, was the century of the Industrial Revolution. And that, of course, changed our world. It also made a lot of difficulties for a lot of people, but nonetheless, it was an enormous change in the world. Because things were changing so rapidly, people like Faraday, people with scientific or technical knowledge, were called upon by government a great deal to give advice and to serve in consultation. And Faraday was in all sorts of things, providing advice for the Admiralty, for the Home Office, for the Board of Trade, etc. And in particular, he consulted a great deal on the invention of the telegraph. And telegraphy made a huge difference in the world because the telegraph was invented just about the time that Britain was involved, and France as well, were involved in the war in Crimea. And because of telegraphy, reporters in Crimea were able to give up-to-date reports of the battles that were taking place in Crimea. And so these things got published in the British newspapers the day or so after an actual battle. And for the first time in history, people began to get an impression of how horrific warfare really was, because the reporting was really of the casualties and the grimness of war. And that made an enormous difference, of course, in our modern reactions to warfare. He was also called upon following a dreadful coal mine accident in County Durham, in which there was an explosion which killed 95 men and boys, because there were a lot of boys working there as well. And that was due to a gas called fire damp in his day, which we call methane, and of course is a highly flammable gas. He also was hugely involved with changing the lighthouses on the coast of Britain from fires to electric lights. He wrote more than 400 papers in his lifetime. He discovered the relationship between magnetism and electricity. He created electric motors. He investigated a thing called diamagnetism, which is a funny property. We all know about ferromagnetism, which is the attraction of iron to magnets, but there are also some materials which are not attracted to magnets, but rather repelled by magnets. And that phenomenon is called diamagnetism, which was discovered by Faraday. He discovered how to liquefy gases, and he discovered a very important chemical compound named benzene. He was also a deeply religious man, and he belonged to a very small Christian sect called Glassites or Sandemanians, after the founder John Glass or his son-in-law Robert Sandeman. It was in that it was really crucially important in his life. He never worked on Sundays. This was a closely knit group. Well, anyway, he was an elder in that church most of his life, but because of his exposure to difficult chemicals, particularly, well, anyway, to various mercury chemicals, he started to lose some of his intellectual ability in old age. Nonetheless, he had created so much that Queen Victoria gave him a house to live in Hampton Court, where were her palaces. And he died in 1867 and was buried in Highgate Cemetery. Michael Faraday and his wife Sarah buried there also. This is in Highgate Cemetery, which is very close to where I live, and is a shrine I like to visit from time to time. He saw no conflict between his religion and his science, which is a little strange because the 19th century in which he lived was the time when Charles Lyell showed from geology that the Earth was not 6,000 years old, but is now, as we know, 13.7 billion years old, considerably older. And of course, it was also the time when Charles Darwin was causing enormous controversy with religious groups. None of these, I mean, these are out of the scope of Faraday's science, and so none of them really seem to have much of a reaction on him. His notebooks are, some of which I've actually read, are in 7 volumes. And they are full of pictures of things that of experiments that he had done. We produce now electricity in many, many different forms in many power stations. We have oil-fired and coal-fired, both of which I hope we can get rid of these days, in hydroelectric and wind power and wave power, in solar power and nuclear power. They all use heat energy or mechanical energy or nuclear energy to create electricity. Solar power works in a completely different way, but every other method we have of generating electricity comes from the conversion of mechanical energy from some form into electrical energy, and they were all invented by Michael Faraday. There are few human beings, I think, who can make such a claim on modern science. Any appliance we have, the CD players or kitchen mixers or electric razors, all of these things that have electric motors, all invented by this shy young man from Elephant and Castle who dropped out of school at 13 years of age. So I think I've run out of time, so I will stop. But tomorrow I want to talk about James Clerk Maxwell, a mathematical genius in the same sense that Faraday was an experimental genius, and who put the mathematics to the technology that Faraday discovered. So thank you very much for attending on such a great rainy day.